if you have a chance to take a look at the diffusion model, you might find here's usually it's given. Okay, you don't need to set up. This it's so-called variance schedule. Okay, covariance schedule. It will apply to each diffusion time step. Okay, that's the beta. Okay, it's another variable, but usually the model or the programming code you use is just by using default. Okay, unless you cannot satisfy your application, then you can change it. Okay, it's. But if you have a chance to take a look at, it's very much just like VAE. Okay, just like VAE, given something, then you estimate the other one, then it all assume the observed value will follow Gaussian distribution. That's it. Okay, so you need to estimate. Okay, when you put theta here, it means you need to estimate the mean and the standard deviation, just like VAE, right? Okay, from the encoder. Then you train the neural network, okay, which theta represents the parameter or the structure that you are going to run for the neural network. So that's it. That's the basic idea. Okay, so from t, given xt, then I want to estimate xt minus 1. So eventually, this xt could mean a noise image, all right? And xt minus 1 will be the less noise, okay, image. And eventually, I will put it back to x0. That will be the final recovery image. So that's the idea, okay? So as you say here, you say that the running basically is very similar, just like VAE, okay? But you need more process, okay? So if you are interested, you can take the look, okay, for the reconstruction of the diffusion, okay? So it's good, okay? It's so the only concern is about the computation time, okay? This is something. You don't say why when you use a mid-journey or something else, you might think it's so fast, but there's a report whenever you generate an image, okay, from the mid-journey or something, just one single image, just like you need to a full charge of your smartphone. Okay, I mean you are consumed the power, okay, to charge your smartphone up to 140 powered. Okay, so it's quite. It takes a lot of computation time for that. Okay, so you can find the detail from the supplementary work. Now I'm not sure if I have. Apparently, I see that I include the flow base. Okay, I won't say anything. The flow base model, but apparently I don't have. I don't have the mask. Okay, let me just give it quickly. You do have in your material, okay, handout material, have a mask autoencoder, right? Yeah. Okay, it's developed by He Kai-ming. Okay, let me just say something about the idea. Okay, not good. Oh, by the way, the original paper for the diffusion autoencoder, the model is based on UNet. Okay, if you know nothing about UNet, I will mention that, okay, right away. Okay, it's based on UNet. Okay, a UNet model is encoder-decoder, okay? encoder-decoder model. Now, about the mask. Autoencoder. Basically, nothing to do with the architecture, but in Herkimin's original paper, the math autoencoder is based on transformer. Okay, it applies, but it does not mean you need to use transformer. You can use any CNN model or LSTM model or anything model. That'll be fine. Okay, that'll be fine. The idea is again, we have an encoder and we have a decoder. Whenever I say we use autoencoder, which means the input should be the same as the output. Okay, the input the same as the output. We input an image. The mask means what? We randomly block some regions of the image, random. So for this application, first you need to determine what should be the mask size. I say mask 就是把它遮罩，把它遮起来。Okay， 遮罩，意思是遮罩 is the mask. We cover when you say mask. It means I put 0. Okay, I put 0. It's a whole black in random region. So for the user, first you need to determine what should be the size. What should be the size of the mask, right? You need to determine the size of the mask. Then the next, what should be the number? Or the percentage you want to mask in terms of the whole image, the mask size, and the number of mask. That's it. Okay. The only, but actually, the original chat GPT use it run the sentence or run the text information. It still use encoder, decoder. Okay, I didn't say it's all, but and the output must be the same, right? It must be the same. And how did it run it? The text. Just randomly block the word. Okay? You know what I'm saying? But I got the standard, right? I have the text, right? No matter it's a download from the blog or any library or anything else. Okay, but when you learn it, for this example, I have a missing word here. I learned it. So later on, you ask something, but you say I, then you might make a guess. So the next word should be am. It may not be true, right? I can follow by what case, you might say, I see a student on campus or something, right? It does not have to be. But anyway, everything is based on probability. And that's why you ask the ChatGPT twice. You may not get exactly the same answer and every time, right? Or you ask with different words or with different sentences, even the meaning is the same, the answer could be a little bit different, right? Right. But that's the basic idea, okay? You make something, and hopefully then you will recover the missing word. We'll get back to that in next semester if you take the data pattern, especially for machine learning. One of the problems is you have a lot of missing data when you collect the data. For example, the medical data, okay? You have all kinds of medical information data about the person, but some person might have, if you collect, for example, 20 features, but some people have 2 or 3 missing values. What can you do to handle the missing value? The most easy way is what? To delete the instance that contain a missing value. But as you know, all the data will cost you. Okay, you need to pay for the cost if you delete it. Okay, so that could be another way. You can go for the mask, autoencoder or something like this. You can learn something from the instance that contain all the required features. And then, just like this, if you have a missing data, then I can use that to estimate what could be the missing value. But it could be better compared to just random guess or just assign 0. Okay, that will be a very important topic in machine learning, especially when you prepare, okay, or you try to clean the features. It's very important. But anyway, go too far. Let's back to but what I'm trying to say is this idea is a loss, okay? But in Herkimer's model, it used a transformer. Okay, it used transformer for the encoder and decoders. I didn't try it, but I'm quite amazing. How many percentage is mask gas? Anyone? What should be a reasonable percentage to mask an image so that you will have a good learning to recover the image?
50%.
550. Don't you think it's too high? No, that's a good guess. 10. 10 or 20 could be a good. Some say 30. In Herkimer's side, it's up to 75. I don't know why. I mean, you just present only 25%. I mean, it removes 75%, okay, mask. And also, it uses a regular, for example, divided into grid, and I remove, for example, regular, okay? That makes sense, right? But it failed. So everything got to be random. Got to be, because when you get a regular pattern, it will give you some unknown fixed pattern for that. Of course, the mask or the number, the percentages for each one, you will try a lot of different times, just like the data augmentation. You won't use a fix. Okay, for each input image, you don't just try out, for example, 20%. No, you will use a lot of different render, and they find out it's better than the regular pattern. Okay, that's the only thing I would like to say, but it's good. That's another way. And what I'm thinking, I didn't prove it yet. If we go for this, especially for manufacturing inspection, maybe all the required training sample can be very, very limited. 比如说你只要用10张或5张 because for example you only have 5, even you only have the normal sample, just 5. And you can think of the mask image randomly. You can repeat it 100 times or 200 times, right? It might also give you a good or reliable autoencoder, okay? For the application, it does not need to be. You need to collect 1,000 or 2,000 or even 100 or some hundreds of sample, but in this case, you can randomly mask from the same, okay, from the same image. That would be something worth trying yet for some application, but that's something new, okay, about the proposed autoencoder. As I mentioned, it does not have to be transformer, okay? It does not have to be transformer. It can be a CN before, which means you can just use any the CNN model that you are familiar with, and the only thing you need to do is just work on the input image to determine what should be the mask size, what should be the number, and remember, it got to be random. Okay, got to be random. And even for random, you might think of, should I go uniform distribution? I say uniform distribution, I didn't say go like this. I mean, each location has the same probability, or it should go for a Gaussian distribution, okay? The location will have follow the Gaussian distribution. That's something you can think of, okay, to do it. Okay? So that's all I want to share with you for autoencoder. Okay, so that's it. And now we can go back to our next topic, which will be semantic network. Okay, semantic network. For image segmentation, okay, let's talk about the image segmentation. It's a very important topic. And usually, if you remember, when we talk about a conventional or computer vision for segmentation, you have learned what? Region growing, right? And from your assignment number 1, the most easy one, it will be thresholding, but it's quite limited, right? And you have learned mean shift, right? Mean shift smoothing. That will be a lot of traditional way to do the segmentation, but it is a very difficult job especially you need some real-time application, just like ADAS, right? When you look at the street scene, you need to identify where is the road, where is the pedestrian, where are the cars, where's the buildings, right? Where the tree and so on. And you need to do it in real time. That will be a very challenging thing. But now that we got the deep learning, everything becomes easy, okay? And we can do it, okay, effectively and very efficient, okay? But the only thing you need to take is how to do the labeling. And pixel-wise label. When I say pixel-wise, you need to identify, because we talk about segmentation, which means you need to mark. For example, where is the pedestrian, right? So where is the person here? Of course, if you don't do it pixel by pixel, at least you need to what? Find the boundary of the object, right? That's one of the things. And you need to find where is the if the driveway or anything else. Basically, it's a pixel-wise notation, which is very, very tedious, okay? So even in the early development of ADAS in Tesla, they hire people from Africa to do all the labeling work, okay? But once you collect some of the label image, then you can go for semi-auto labeling. And all the person they need to do just to double check if the results okay, or just do some minor modification, okay? I don't know, I still feel the TA give you the old version of everything. Because I did remember oh, okay, it's here. If you want to know more about how Tesla trained their ADAS system, okay, here's some information they use. Okay, the best model and a lot, and how they do their labeling. Okay, so I won't give the details. They just based on their presentation. Okay, a Tesla. A forum, they give you a lot of details, information, how they do this. Okay, so it can give you a lot of good information for their application. Okay, so anyway, let's go back to the segmentation. Okay. If I have only one choice to do the image segmentation, from my point of view, UNet will be my only choice, okay? Based on its performance. in terms of the segmentation accuracy, in terms of the computation time of training and test. Okay, it's very, very efficient and very effective. But before that, I still need to talk about the kinds of history, how the image segmentation developed, okay, using deep learning algorithm. But pay more attention on UNet or DenseNet, okay? DenseNet usually can outperform UNet, but the training time and inference time could be more than UNet. Okay, that's what I'm saying. If you want to keep the balance between the computation efficiency and the segmentation quality, UNet could be a best choice. And after UNet, there's a lot of UNet variant model, some called U2Net. I mentioned that before. Okay, it's a UNet in a UNet. Okay, or UNet Plus and UNet double plus a lot. Okay, if other time I will mention the idea, but for me, all the model developed after UNet are too complicated, and the improvement could be minor. Okay, could be minor. I mean, the improvement could be only 1 or 2%. Okay, in the segmentation accuracy, but pay more attention on UNet and DenseNet, and I will introduce some additional one, which is developed in just last year, called DeepLab. Okay, now DeepLab have DeepLab 1, DeepLab version 2, and now it's DeepLab version 3. Okay, but before that, let's talk about all this. Okay, the very first one in the early day, anyway, the semantic model, the semantic network model, it got to be, must be in the form of encoder and decoder. 它一定有编码跟解码 okay? It must be contain encoder and decoder. But not like the autoencoder. The input could be X, the output could be another image, Y. But for our application, Y will be the segmentation result. Y is not a class, okay? Y is another image. It will be another image. If we input an image, X. So basically, this structure can be applied for, especially for the so-called image to image translation. So actually, segmentation is one of the applications for image-to-image translation. We can think of the segmentation result as another image. But for image generation, the so-called image-to-image translation have a lot of different applications. For example, the input image could be a black and white image, and the output will convert the black and white image or picture into a color picture. Now that's some of the idea. The original movie, okay, the film of a movie, could be 80, 60 years ago. at that time, the color technique has not been developed yet. And nowadays, you can see some of the picture 100 years ago in the Qing dynasty, for example. You can see it becomes color. That's it use these kinds of technology, the so-called image-to-image translation. If you train a lot of black and white and show that color, you might wonder, in the Qing dynasty, there's some black and white image. I don't have the corresponding color image. How can I set up the ground truth? How? 为什么清朝上只有黑白影片？那我现在怎么去训练彩色影片？都没有成对啊，那我怎么训练？ Don't forget, the training can go in the reverse way. It's much easier to convert a color image, just like when you're doing the assignment, right? You can always convert the color image into a black and white, right? 是吗？你拿到彩色影像容易吗？彩色转黑白容不容易？ You don't need any deep learning to convert color image into black and white, right? Right? You don't need it. Right? You just take out plus GMP, for example. But of course, how you convert the one color to black might affect then the reverse way to convert black and white into a color image. But anyway, a lot of things is based on your imagination and how you do the training. For this case, you got to collect the color image and then use the traditional way to convert it into black and white. Then train the black and white and use the color as the ground truth. And after that, you can input any black and white. And you might see some. Because when you do the training, if the image contains the tree, then the color got to be green, right? With that. Should be green. So you can, you will learn the relationship, okay? The tree and the street, or the color of clothing, it may not be. That depends on the data you train, and you can see how close the black and white can convert into the true color in the real world. But anyway, there's a lot of things you can do. Okay. Anyway, based on the encoder decoder. Okay. The deepfake 那个换脸 is based on encoder decoder. Okay. I input the face, I convert it into. For example, I input, I train a male and convert it into a female or anything else. Okay, that's also the image to image. Or you can input a hand drawing, okay, the sketch of a picture, then I can convert it into a painting. 你可以素描转成油画。 Right, then you can do it all. If don't have the hand drawing, again, you can get a real color painting, and you can use any image processing tool to find the sketch, right? Find the edges, for example. That would be easy. That's one of the reasons why you need to learn some of the traditional image processing. Okay. Otherwise, the image-to-image translation could be very difficult to prepare the training data set, okay? Because they must be paired, okay? I will talk about the non-paired image-to-image translation by GAN, okay? By GAN. I was mentioning something like that. But anyway, for the semantic network, for image segmentation, the model got to be encoded and decoded. 解码, 编码, okay? Okay. And usually, the encoder model, that's what I'm saying at the beginning today. I need to mention VGG one more time, because most of them is, if you apply the neuron, the CNN model usually is based on VGG or residual net. Okay, and even you use a pre-trained VGG, just what you have done in assignment number 4, you use a pre-trained model. So no matter for VGG or residual net, okay, you can use it. And now you might think of to use convolutional net. Okay? So that's it. Okay? The encoder, usually we just simply go for VGG or residual net. Now, let's discuss the very first. Nowadays, not too many researchers use this model, but you still can find it. Okay, still can find it in some of the model because it's simple. Called FCN means 40 convolutional network. Just 40 convolutional, so no dense. Not 40 connected, okay? 40 convolutional network. Let's see how it works. Here's the input. And you see the convolution layer here, okay? The size getting smaller, okay, because after the convolution, the size will become smaller and smaller, and at the end, it enlarges. It just enlarges, okay? Not quite just like the encoder decoder, or if you want to, it's branded as an encoder decoder architecture, which means the number of layers for encoder and the number of layers of decoder, they are not symmetric. 它没有对称. Okay. And they don't have to be symmetric. Okay? I mean, the number of layers, if you go for the CNN, the number of layers for encoder does not have to be the same as the number of decoder. But most of the time, we will use a symmetric architecture, which means the number of encoder will be the same as the number of decoder, especially for UNet. I will explain why. Okay, why you use that. But for any other model, encoder, decoder, the number of layer or the depth does not have to be the same. Okay, but in most of the cases, we will use the same number of layer for encoder and decoder. But for this one, almost you don't see any decoder, but it just use encoder. I mean the size or the feature map getting smaller and smaller, and at the end it just enlarges the image. Okay, so this is the input. This is the segmentation. Now that's why the user need to do the manual annotation. That will be very tedious job. Okay. Okay, let's see how it do it. Okay, how it do it. Let me first state it, because after the convolution, the image will getting smaller and smaller, and at the end you need to enlarge it, right? So you need to do the upsampling. In the original paper or the original source code, you use bilinear interpolation. Okay, you use a bilinear. Of course, if you want, you can replace it with bicubic. Okay, or any better interpolation. But anyway, the original source code uses a bilinear interpolation for FCN. Okay. For our application, we are not interested for classification. Instead of we want to do it for segmentation. Now, let me show you the architecture here. Okay. Here's the input. Okay, the original input image. Then this is the cementation result. Okay, the final cementation. Now take a look about the architecture here. You go for the two convolution. Okay. Well, actually, you look at very closely, except for the max pooling. It looks like what? Convolution, 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 convolution. Oh, also you have the max pooling. I'm sorry. Two convolution connect to, then followed by pooling. Two convolution followed by pooling. Three convolution, three convolution. So what is the architecture? What? I just mentioned it, right? What is architecture? BGG. Okay, a standard BGG. A standard BGG architecture. Okay, then that's it. We have a two convolution layer, then pooling. Okay, with us try to up 2, which means we will reduce the size by 2. Okay, by a factor of 2. Then 2 convolution. Okay. Then 1 pooling, and then 3 convolution and pooling. So after pooling 1, you will reduce by 2. After pooling, you will reduce further, but it will be 4. The factor will be 4 compared with the original image. Everyone follow me? 也就是说它这边会减少2倍，这边变减少4倍，相对原来的尺寸。Okay, so you will go for 2, 4, okay, and then 8. Right, and 16. See that? Everything, okay? And then 32. 2, 4, 8, and 16, 32. And after that, you need to do the upsample to bring you back to the original image, right? 因为它被缩小了嘛。我刚刚讲4、8、16。好，2、4、8 ，OK， 16到32，它最后要还原到原来的尺寸。So that's why you put 32 here. Okay, you will upsample by a factor of 32. But because it didn't go for a lot of deconvolution layer, okay, it just go, see that? Just convolution, everything just like VGG. But at the end, it upsamples, so you know the recover or the cementation result got to be very, very rough. Okay? It cannot maintain the details, but it will show the overall regions. 可是那些细节一定不见了。But again, depends on your application. Don't care about the detail. This will be fine. So anyway, when you apply the 40 convolution model, it provides you 3 different versions. Okay. Now take a look at the second one. The second one here is again 2, 4, 8. 16. Okay, so it skip this operation. So you put it here. Okay, so this is 16, and then it connect to the convolution 7. You do the. Everyone follow me? Okay. Of course, you need to do the upscale. Okay. Upscale by 2 because it has been reduced by 2 upscale. But for this case here, you need to go for upscale by 16. Everyone understand what I'm saying? 好，也就是说，因为刚刚讲32呢，这边呢太粗了，所以呢，它在 pulling 4的时候呢就接过来，然后呢后面呢直接接 pulling 7。But the size of pooling 7 must be upscaled by 2. Okay, upscaled by 2. And then we upscale by 16. to bring it back to the original size. Now note, the segmentation result is better than upscale by 32, but may not be good enough. So there is another purpose. So we do the connection from 3, which is 2, 4, 8, right? 8. We reduce in a factor of 8. So we put it back here, but in this case here, we still need to go with pulling, okay, pulling 4. Okay, upscale the pulling. We still need to upscale, okay, because the original here is pulling 3, then we add the pulling 4, the result pulling 4. We need to upscale by size of 2 so that they will have the same size. And also we need to upscale 4 by a factor of 4 for convolution 7. And eventually, you need to do the upscale by a factor of 8. Okay, so now you can get some better segmentation for the details. And of course, if you want, you can write your own. You can do the fully connected from here. Okay, or from here. I'm sorry, from here, right? And then you can double chart. But in the original model, it provides the upscale FCN 8, 16, and 32. Then take a look of it just keeps saying what I'm just saying. Okay, pulling 3, pulling 4, up to pulling 5, and you need to upscale by 32. That will be the FCN 32. Okay, the other one is when you go for the pulling 5 here. Okay, then we do the upscale by a factor of 2, and the pulling 4, put it here, and here we can do. Okay, we sub-length up. Okay, we sub-length up. We don't. It's not based on concatenation. Okay, 还有加法。Okay, element-wise, addition. They just sum up, okay, the corresponding element value, okay, and put it here. And this is the same here, okay, the same here. We just sum them up, okay, just sum them up, okay. Back to here, everything here. We just sum them up, okay, just sum them up. Before that, you need to do the upscale to make sure they have the same size. And then we do the element-wise, okay? I don't call it pixel because the feature map, because you might misunderstand, okay? Or actually you call it pixel-wise, addition will be fine. But we prefer you call it element, okay? Because each pixel in a feature map is called an element, okay? Instead of a pixel, okay? That's how we get, okay, for the FCM. But some of the model, not just for segmentation, they still use this simple architecture for that. But if you care only about the segmentation, usually we don't take this approach because the result is not good enough, okay? Because we see a lot of encoding, but there's only one decoding, which is upscale, okay, upscale by 8, by 16, or by 32. So that's the result. Let me show you here's the result. Okay, this is the ground truth, okay? It's the bicycle here, okay? So for the FCN 32, you can only see different color represent different region. Okay, the black is the background. Okay, and green represent the bicycles. See that? But for FCN 8, it's getting better because you can see the handle, right? You can see the handle of the bicycle, right? And It's nothing much too different between 16 and 8. So if you want to have a better result, maybe you need to go to FCN 4, for example. Okay, for that. But anyway, that's the application. It's an easy, simple model. So people still use it, okay, as additional information, especially for classification. Basically, they just use for classification, but they provide this additional information for localization. To show you where is the object. That's it. Okay. Okay, that's FCN. So let's take a break, and next I will talk about UNet. Okay, that's the one used a lot. Okay, and I highly recommend it, especially for manufacturing application, because it's easy to train computationally very fast. Okay, let's take a break.